Welcome to your lecture on thermochemistry, phase change energy diagrams. For this lecture, you definitely need a pencil, pen, and some paper. Pause the video where you see necessary. Make sure that you write down the critical content that will be pointed out for you to know. These calculations need to be done repetitively on your part. We are going to go through some of the terminology for phase change energy diagram so you understand what we're talking about. But as we go through these problems, make sure you're following along, pausing the video if you need to, just to make sure you understand the process. If you have any questions of understanding and clarity, please make sure that you write those down, and hopefully we'll have them answered by the end of this lecture. If not, please make sure that you meet with your instructor and get that clarity, get that understanding before you take the assessment for this unit. So let's get started. We all know that there are phase changes. There are three major phase changes: the solid, the liquid, and the gas. And there are some other phases of matter that have been brought to the forefront. But those are your three main phase changes. Those phase changes require energy. Kinetic energy is the energy of motion. And notice, if you will please, that its symbol is Ke, so wherever you see Ke. But kinetic energy, we're talking about moving energy, the energy of motion. Make sure you understand what kinetic energy is. The kinetic theory says that all particles of matter are in motion. So one is the kinetic energy itself, what kinetic energy is, which is energy of motion, and then there is the kinetic theory that particles of all matter are in motion. Make sure you know the kinetic theory. Let's look at the three main particles. First one we're going to look at is a solid. Solid particles are in a fixed pattern. That means that they are tightly packed. They have very little movement, which means they have a low kinetic energy with very little movement. And they vibrate around a fixed point. Why? Because those particles have energy in them. Remember we talked about potential energy, PE? Potential energy. The potential energy is locked into this solid. That energy wants to get out. So while that energy is in there, while there's very little movement, there is a high potential energy holding those particles in that fixed pattern. And so they're vibrating to get out. This vibration is what we call vibrational energy. How do we demonstrate vibrational energy? If you clasp your hands together and start shaking, moving your hand back and forth, shaking as if you're trying to pull your hands apart but can't do it, that is a demonstration of vibrational around a fixed point. Make sure that you know this information. So make sure that you understand that solid particles have a fixed pattern. Also that they are tightly packed. They have very little movement, which means the Ke is low. And they are vibration around a fixed point, which is vibrational energy. When we look at a liquid particles flow past each other. So there's some energy, but they stay close to each other. So they have enough energy to move a little more than solid, but they stay very, very close to each other. They are loosely packed. They have medium kinetic energy because they have a limited amount of movement. But not only do they have the ability to move around each other, they've still got that vibration around a fixed point because they've got that limited movement, and they rotate around each other. So a liquid has what we call vibrational energy. And it has rotational energy. How do we demonstrate that? Pretend you're washing your hands. Notice as you wash your hands are breaking contact and coming back, breaking contact and coming back. That's an example of how particles flow past each other but stay close to each other in a liquid. So make sure you understand the difference between the liquid and the solid. Whereas the solid is tightly packed, the liquid flows past each other and are loosely packed. Remember that the solid is around a fixed point. Remember that the solid has very little to no movement, so they have a low kinetic energy, whereas liquids have limited movement, so they have a medium kinetic energy. Remember that a solid has only the ability to vibrate around a fixed point, but a liquid can also break loose a little bit and come back together, so they have the ability to rotate around each other. And we have gas particles. Gas particles are far apart from each other. So as opposed to being limited in movement or flowing around each other, they collide with and rebound off of each other. Their movement is very rapid, so they have a high kinetic energy. And they have both vibrational and rotational with them. And they have what we call translation motion. So gases have vibrational. Remember, those gas particles have to break apart, so they're close to each other. Vibrational energy, they have rotational energy because they do move around, and they have translational energy. Translational energy is the ability to break loose, to go up from. Okay, make sure you know about gases. Gas particles are far apart from each other. Liquid particles flow around each other. Solid particles are around a fixed area. Gas particles collide and rebound off each other. Liquid particles are able to break apart and come back together. Solid particles don't break apart at all. Gas particles have a rapid movement or high kinetic energy, which means they have low potential energy. Gases have medium kinetic energy, as well as medium potential energy, and solids have very low kinetic energy and high potential energy. Gas particles have vibrational, rotational, and translational motion. Solid particles have only vibrational. Liquid particles have vibrational and rotational around each other. So this is what we call a phase change diagram, where you're going to find your solid, your liquid, and your gas. The phase change diagram allows us to determine the changing of phases and the amount of heat that goes into each phase, as well as temperature change. We already know that solids have vibrational energy. So if I look at the heating of a solid, if this is my heat energy, amount of energy going into the substance or going into the change, and the temperature, of course, is rising. If I look at my solid, as my solid increases in temperature, notice that my temperature is increasing also to a particular point. This is a change in temperature. Okay? Now, when we get to going from a solid to a liquid, here we have the same thing with liquid. With liquid, as the liquid temperature goes up, as the liquid is being heated, heat energy is also being put into this liquid. So you have it like an incline, whereas here you have an incline with the solid because you have both temperature going up and you have heat energy going into it. Here you have an incline with the liquid. This is where vibrational, rotational energy is. And then you have your gas. Again, gas takes in heat energy, but the temperature is also rising with the gas. So with gas, liquid, and solid, you have a temperature change occurring from wherever the temperature was to the end of where that solid is solid. Same with the liquid and the same with the gas. This is a delta. Delta means change. So here we see a delta in the temperature or a change in your temperature, and I would denote that with a delta T here, a delta T here, and a delta T here. This is my temperature change. Where freezing and melting are occurring, there is a movement and an increase in heat energy, but notice that the temperature does not change at all. All that's happening is heat energy is going into the system. Now, what does that heat energy do? Well, that heat energy is changing the solid into the liquid. So I'm going to put that right here. It's used to change solid into liquid. What does that mean? That means if I put ice on a heat, and if it was contained heat, that ice would heat up into the point where it could actually change from ice to liquid. The temperature then would stay there until all the particles of the ice or all the particles of the solid have enough energy to make the whole thing liquid, and it would stay that way until the entire substance has reached liquid form before it starts heating, because once it starts heating, now it's going to be heating the liquid. There is no temperature change because all the heat energy that's going into this is going in to change the solid into the liquid. When the solid heats itself up to a particular point, it reaches boiling point. Again, if I had water in a container and I heated the water up, once it reached the temperature of boiling, it would stay at the temperature of boiling, because at this point, this heat energy is being used to change my substance from liquid to gas. No temperature change is occurring, but this is changing from liquid to gas. And then the substance would continue to heat. So, what's going on here then? To recap, I can heat up a solid to a point where it is going to start changing into a liquid. Temperature will increase, heat energy will increase. At a particular point, which we call melting, that solid is going to continue to accept heat energy, but my temperature is not going to change until it becomes a liquid. Once all of it has become liquid, then the liquid will start heating itself up. Again, the temperature change will occur as energy is being put into the system. Once it reaches to where that liquid starts to become gas, there will be no temperature change until all that liquid has reached the gaseous phase. Once it's reached the gaseous phase, then my gas will continue to go up and my temperature will continue to go up with heat energy. So heat energy then not only is put into the solid, liquid, and gas to heat the solid, liquid, and gas, but it is also put into the place of where the solid, liquid are going to transfer, the liquid and the gas are going to transfer their phases. No temperature is necessary, but heat energy continues, and that's used for the purpose of changing the solid to a liquid and the liquid to a gas. So what happens if I go in the opposite direction? Very easy. In the opposite direction, I will continue to decrease the heat on my gas until it reaches a point where the gas starts to turn into liquid and condensation. Then temperature will stay the same. However, my heat energy, which is now no longer rising but is decreasing, heat energy is being lost until that gas condenses into a liquid. Once all of it has turned into a liquid, then the temperature of my liquid will start to go down until it gets to where the liquid can freeze. heat energy is being lost as well as the temperature dropping. Then it reaches a point where melting occurs, where heat energy continues to be lost. Temperature does not change until it reaches all solid. Once it's all reached solid, then the solid temperature will continue to decrease. That is a phase change diagram. Now, phase change diagram is used for all substances that we'll be doing in these problems. The first thing you have to have, though, is your visual, which is your phase change diagram. Once you understand your phase change diagram, then you'll be able to use it in the application of determining how much energy goes into or out of a substance as it changes its state. So pause the video for a moment, write down whatever questions you may have. When you're ready, go ahead and start the video again. So here we're looking at a phase change diagram. Could be any. This particular phase change diagram, it has the melting point here. Remember, melting is also freezing. It has the boiling point here, which is also condensation. Here we know is a solid, this is a liquid, and this is a gas. So the melting point of this is somewhere right here. Let me do that better. And the boiling point is about right here. So let's answer these questions. What is the phase of the substance at point A? Well, point A is a solid. Because point A, let me clear this out. There we go. Point A is a solid because point A is where the solid lies on the phase change diagram. What is the phase of substance at point B? Remember, at point B we have melting and freezing. So that's what's going on. It's in a solid and liquid state until it either becomes all liquid or if it was decreasing in temperature until it becomes all solid. What is the phase of the substance at point C? At point C, we said this is where our liquid is. What is the phase of substance at point D? Here is when the liquid becomes gas or the gas reduces down to liquid. So this is boiling and condensation. Here you have a mixture of liquid and gas together. What is the phase of the substance at E? We know to be gas. That was kind of easy. What is the freezing point of the substance? We said the freezing point is about here. So I'd say, let me see if this is 0. 20 to 15. I would say 0 is about there. That's 15. So maybe 14 degrees. Remember, this is 0. What is the boiling point of the substance? It's right here. It's about 128, 127. Not quite complete. 28 degrees Celsius. See why? Because it's right there. What is the melting point? The melting point and the freezing point are the same. So that's like 14 degrees Celsius. Maybe 14, 15 degrees Celsius. What letter represents the range where the solid is being heated? Well, solid is being heated here. So that would be A. What letter represents the range where the liquid is being heated? Liquid is being heated here. So that's going to be a C. What letter represents the range where the gas vapor is being heated? Gas is being heated here. So that's your E. What letter represents the melting of the solid? Here is where melting and freezing occurs. So that would be B. What letter represents the boiling of the liquid? Boiling condensation is here. So that would be D. What letter shows the phase where the highest entropy is reached? Okay, you should already know what entropy is, but entropy is disorder, right? So if I'm going from a solid to a liquid to a gas, and I'm looking about disorder, which one of those has more disorder to them? The solid, the liquid, or the gas? The solid has little to no, very little kinetic energy. Liquid has medium kinetic energy. Gas has high kinetic energy. Which one has the bigger ability to have chaos? If you chose gas, then you're absolutely correct. So we want to know where the phase with the highest entropy is reached. That would have to be the gas phase. So we're going to put E, because that's where gas is. What letter is where the lowest entropy is reached? Well, we know solid barely has any ability to disorder itself because it's locked around a fixed point portion. So this is going to be the solid, which is A. What letter is condensation? We said condensation is up here with boiling, so that's D. And what letter represents crystallization? Crystallization is the same thing as freezing, so we said that would be right here, so that's going to be B. Now what is happening to the temperature at point A? If we look at A is going up, so our temperature is increasing. I'm going to put an up arrow. What is happening to the energy in the system at point A? Well, as point A goes up, this is also moving forward, so this is also increasing. What is happening to the temperature at point B? At point B, we see that there's no increase in temperature, so it stays the same. What has happened to the energy? Well, as the temperature stays the same, we're still moving forward with that energy. So the energy is still increasing. What has happened to the temperature at point C? Point C, the temperature is going up. And here the temperature is rising with it. So that's increasing. What has happened to the energy in the system at point C? As C increases, that energy is still going up. What has happened to the temperature at point D? At D, there's a flat line, so there is no temperature change. So we said the same. What is happening to the energy in the system? Even though the temperature hasn't changed, that heat energy is still going forward. What is happening to the temperature at point E? As the gas temperature is increasing, our temperature is still going up. And the energy, as it's increasing, the heat energy is still going forward. Okay? So pause a moment, make sure you understand the answers that we have put in place. And then press play and go on. This is a great spot where you could write your questions down if there's anything you just don't understand.